Analysis of variance examines the relationship between a categorical explanatory variable and a quantitative response variable, and was the first inferential tool we looked at. The chi-square test of independence is an inferential tool which examines the relationship between two categorical variables. If you have a quantitative explanatory variable and a categorical response variable, for the purpose of this course, we encourage you to categorize the quantitative explanatory variable and use the chi-square test of independence to examine this type of association. The next inferential tool we're going to look at is used for examining the association between two quantitative variables, the Pearson correlation. We previously discussed that a scatterplot is the appropriate way to graph or visualize two quantitative variables when you want to examine the relationship between them. Let's first briefly review scatterplots and how to interpret them. To create a scatterplot, each pair of values is plotted so that the value of the explanatory variable, x, is plotted on the horizontal axis, and the value of the response variable, y, is plotted on the vertical axis. In other words, each individual appears on the scatterplot as a single point whose x-coordinate is the value of the explanatory variable for that individual and whose y-coordinate is the value of the response variable. When describing the overall pattern of the relationship, we look at its direction, form, and strength. The direction of the relationship can be positive, negative, or neither. A positive or increasing relationship means that an increase in one of the variables is associated with an increase in the other. A negative or decreasing relationship means that an increase in one of the variables is associated with a decrease in the other. Not all relationships can be classified as either positive or negative. The form of the relationship is its general shape. When identifying the form, we try to find the simplest way to describe the shape of the scatterplot. There are many possible forms. Here are a couple that are quite common. Relationships with the linear form are most simply described as points scattered about a line. Relationships with the curvilinear form are most simply described as points dispersed around the same curved line. By definition, the correlation coefficient measures a linear relationship between two quantitative variables. So at this time, we won't be concerned with curvilinear or any other possible forms a scatterplot may take. The strength of the relationship is determined by how closely the data follow the form of the relationship. These two scatterplots display positive linear relationships. The strength of the relationship is determined by how closely the data points follow the form. Data points on the left scatterplot follow the linear pattern quite closely. This is an example of a strong relationship. Data points on the right scatterplot also follow the linear pattern, but much less closely. Therefore, we can say that the relationship is weaker in general, though assessing the strength of a relationship just by looking at the scatterplot is quite problematic. We need a numerical measure to help us with that. The numerical measure that measures the strength of a linear relationship between two quantitative variables is called the correlation coefficient and is denoted by a lowercase r. The value of r ranges from -1 to +1. Not surprisingly, negative values of r indicate a negative direction for a linear relationship between the two variables, and positive values indicate a positive direction for the linear relationship. Values that are close to 0, whether they're negative or positive, indicate a weak linear relationship, and values that are close to -1 or close to +1 indicate a strong linear relationship, either negative or positive. A Pennsylvania research firm conducted a study in which 30 drivers of ages 18 to 82 years old were sampled. For each one, the maximum distance in feet at which he or she could read a newly designed sign was determined. The goal of this study was to explore the relationship between a driver's age and the maximum distance at which signs were legible. The explanatory variable is age, and the response variable is distance. Here's a scatter plot for the data, which shows a negative linear relationship between the age of a driver and the maximum distance at which a highway sign was legible. What about the strength of the relationship? It turns out that the correlation between the two variables is R equal to negative 0.793. Since R is less than 0, it confirms that the direction of the relationship is negative. Since R is relatively close to negative 1, it suggests that the relationship is moderately strong. In context, the negative correlation confirms that the maximum distance at which a sign is legible generally decreases with age. The correlation only measures the strength of a linear relationship between two variables. It ignores any other type of relationship, no matter how strong it is. For example, consider the relationship between the average fuel usage driving a fixed distance in a car and the speed at which the car drives. Our data describes a fairly simple curvilinear relationship. The amount of fuel consumed decreases rapidly to a minimum for a car driving 60 kilometers per hour, and then increases gradually for speeds exceeding 60 kilometers per hour. The relationship is very strong as the observations seem to perfectly fit the curve. Although the relationship is strong, the correlation, R, is equal to negative 0.172 and indicates a weak linear relationship. This makes sense considering that the data fails to adhere closely to a linear form. The correlation is useless for assessing the strength of any type of relationship that is not linear, including relationships that are curvilinear, such as the one in our example. So beware of interpreting R when it's close to 0 as an indicator of a weak relationship. Rather, it indicates a weak linear relationship. It's very important to always look at the data in the scatter plot, since, as in our example, there might be a strong nonlinear relationship that R does not indicate. The same can be said for a large correlation coefficient. It's very important to interpret both the scatter plot and the correlation together. As with the other inferential tools we've discussed, an associated p-value is also calculated for the correlation coefficient, and it's interpreted as significant when it's less than or equal to 0.05. Thus, the correlation coefficient and corresponding p-value will now allow us to evaluate whether or not the relationship between two quantitative variables we observe in a sample holds for the larger population.
To demonstrate how to request a correlation coefficient in Stata, let's go back to the scatter plot we created for some of the gapminder variables. We use these scatter plots when visualizing the association between two quantitative variables. The first scatter plot shows the rate of internet users by the rate of the country's population living in urban settings. The second shows the rate of internet users by income per person. From looking at the scatter plots, we can assume that the associations are positive. That is, a higher internet rate is associated with both higher urban rates and greater income. Now, let's find the correlation coefficient. To do this in Stata, we use the command pwcor. The order of the variables actually doesn't matter, because the results will be the same either way. But for the sake of consistency, we'll first provide the quantitative response variable, or dependent variable, followed by the quantitative explanatory variables, or independent variables. The command pwcor, however, only provides us the correlation coefficient and not the p-value. To add the p-value, we need to include the optional argument sig, which is short for significance. So after the code we have written so far, we must add a comma, then the optional argument sig. pwcor, dependent variable, independent variables, comma, sig. And then Stata will give us the following output. The output looks very similar to a matrix in that Stata provides information for all possible comparisons. You can see here that the correlation coefficient for each variable when compared against itself is 1.000, which is to say that each variable is perfectly correlated with itself. This, of course, doesn't tell us anything new. So we really want to focus on the cell that shows the correlation between our independent and dependent variables. Here, I see the correlation coefficient is approximately 0.61 with a p-value of 0.0000. This tells us that the relationship is statistically significant. For the association between income per person and internet use rate, the correlation coefficient is approximately 0.75, and again has a significant p-value. So now, we can actually interpret the scatter plots and the coefficients together. The association between internet use and income is fairly strong, and also positive, as the scatter plot has already shown us. The association between internet use and urban rate is also positive, but slightly more modest at 0.61, meaning that the points are slightly more variable around the linear trend line. Both are statistically significant. That is, for both associations, it is highly unlikely that a relationship of this magnitude would be due to chance alone.
Here's some good news. Post-hoc tests are not necessary when conducting Pearson correlation. Post-hoc tests are needed only when your research question includes a categorical explanatory variable with more than 2 levels. Because our explanatory variable in the context of correlation coefficient is quantitative, there's never a need to perform a post-hoc test. Another interesting and useful aspect of the correlation coefficient is, if we square the correlation coefficient, that is, we multiply it by itself, we get a value that also helps our understanding of the association between the two quantitative variables. Small r squared is the fraction of the variability of one variable that can be predicted by the other. For example, when looking at the relationship between urban rate and internet use rate, if we square our correlation coefficient of 0.61, we get 0.37. This could be interpreted the following way. If we know the urban rate, we can predict 37% of the variability we will see in the rate of internet use. Of course, that also means that 63% of the variability is unaccounted for. If we square the correlation coefficient for income per person and internet use rate, we get a value of 0.56. This suggests if we know income per person, we can predict 56% of the variability we'll see in the rate of internet use. This is a little bit more impressive because we can predict over half the variability. Again, correlation coefficients are commonly denoted with a lowercase r, and they're squared to determine the amount of variability that can be predicted. You might be wondering how much variability in internet use rates can be predicted if we consider both urban rate and income per person. A multivariate inferential tool called multiple regression can be used to answer this question, and we'll discuss that in the future.